today, we're going to look at components of forces. So last time we did some basic theory of what forces were. Now we're going to get to components, and we're going to rely on a little bit of previous knowledge from previous years, and we're going to break our forces up, okay? So that's what we're doing this time, because it's really important for calculations. So, oops. This is our questions. How can an object move horizontally or vertically when the force we're applying to it is at an angle? Okay, so we don't always just push and pull horizontally. Sometimes we pull things at an angle. Or, like a lawnmower, we push at an angle. But the object still moves horizontally. Or, sometimes it can be vertically. So we've got to look at how that happens. And also, why do objects slide down slopes if we just left it? Okay, we know there's gravity, but we also know that gravity is vertical. So it goes vertically down, but objects will go down a slope. These are things we need to think about. So that's what we're going to do today. So we've done properties, types, and representation of forces last time. Today, we're going to look at components, and it went on before I wanted to, but that's okay. We're going to look at the important terms we're going to look at today. Vertical component, horizontal component, gravity again, parallel component, and actually, that shouldn't be vertical, this should be perpendicular. Okay, we're not going to do vertical twice, perpendicular. And hopefully, you recognize the terms parallel and perpendicular from geometry. Okay, this is where we add some maths in. So, we are looking at components. Okay, that's what we're looking at. The first one is when we have an object on a flat surface. Okay, so now what this means here is that the force that's being exerted on the object will be at an angle. Not the object's flat on a surface, okay, and the force is at an angle. Now, whether it's pulling up at an angle or pushing down at an angle, it doesn't matter, but the force will be at an angle. There, we're going to break up the force into a vertical component. Vertical is the one that goes up and down, okay, and we're going to break it up into a horizontal component. Horizontal being sideways, okay? This is very important because when we get to the sections where we look at Newton's second law, knowing these two become important for us, okay? So it's quite important. So let's look at the first one. Here we have a force. Here's my force at an angle. The object is irrelevant at this point. It doesn't matter what this is. The point is that I have a force, size we don't mind, that's acting at an angle theta. Theta is always measured from the horizontal. So it's not random, okay? It's measured from the horizontal. What we want to do is, how do I break this up? So let's start again. So we've got it on a new slide for us. Here's F. When you first looked at vectors, we looked at net forces, okay? So we could tell you there was a tug of war and vectors were acting at an angle, and we said, what's the resultant? Where does it go to? And we added the vectors together. What we're doing is the opposite. That's the net. That's the result. We're now going to break it up. Now, if you look at the arrow is pointing up and to the right. That means there's a horizontal component which is going like this. There's part of this force is pulling it to the right. This is my horizontal component. Part of this force is also pulling it up. Now, I've made that a little bit too long, but it's okay. Oops. Didn't want that. It's going there. there's the vertical. So let's make the horizontal actually sit where it should. We're just going to make it the right size. So there we go. So now we've broken it up into the two sizes. So I can say the vertical force, the vertical part, is what tends to lift the box up. The horizontal part is what makes it go to the right. We have to be able to calculate these. Here, trig becomes important from maths. And I know we hate trig, but it's okay. We can do this, okay? So F is the hypotenuse. So if we go and I say, let's find the vertical, okay? The vertical is opposite the angle. So when we think about our trig ratios, we've got sine, cos, and tan. We're not going to use tan because that needs the two unknowns. We don't know that. So either we're going to use sine or we're going to use cos. Sine uses the side opposite the angle. So sine theta is my opposite side over the hypotenuse. Now we don't like fractions because they're horrible. So we're going to manipulate this to say, well, my vertical force is F times sine theta. So if I know F, I can find the vertical by using theta. But the vertical component is still a force. Force is still a vector. Vector means size. That's what that gives me. And I need direction. The direction must go towards the arrow in the force. So this is a pulling force that's pulling it up. So my vertical force goes upwards. Okay? You can learn this equation. But sometimes they try and trick you with where they put the angle. So I would rather you learned being able to use the trig, okay? That once you've got your right angle triangle, if you know your trig ratios, you can work it out no matter what it gives you. So it's almost like you're learning one less equation because they're not going to give this to you. It's not on your information sheet, okay? The horizontal component, that's this one. Now the horizontal component is adjacent to the angle. It's next to the angle. That means I'm going to use cos, okay? So cos theta is my horizontal component over F. Once again, we don't like fractions. So FH is F cos theta, okay? Again, this equation, this gives me the size. Direction comes from the arrow, and my arrow is going towards the right, so FH must go towards the right, okay? What's important to remember here, F is the hypotenuse. That's the biggest value. Your horizontal component and your vertical component are smaller than F, okay? They're parts of it. Together they give you F, okay? Very, very important. The only thing that can change is instead of making it a pulling force, I make it a pushing force, okay? These equations stay the same. The difference is just the direction. Whether if it's a pushing force, then the vertical goes down, okay? And whether it goes left or right depends on which way that force is going. But it's the same thing. Just for some of you, you may not have been taught it as vertical and horizontal. This here, you may have been told to use this as Fy. Y is just the vertical axis if you look at it from maths. It's the same thing. Fh, you may have been taught as Fx. Same thing, it doesn't matter, okay? I like to use vertical and horizontal so I don't get confused with the maths. It just makes life a little bit easier for us, okay? Flat surface, vertical component, horizontal component. All right, so we've done the one component. So we're still busy with components. Now we're going to look at what happens when we have something on a slope. Now the component we're looking at here specifically is the force for weight, okay? Now slope means that the object is on a slope. So the force isn't at an angle anymore per se, but weight is, okay? Now we're going to talk about a parallel component and a perpendicular component. This has all got to do with the slopes. This is very, very, very important, okay? This comes up all the time. So, this is the situation. We have an object on a slope, okay? This object experiences weight. Why? Because it's on Earth. Weight acts down. It's vertical. The object doesn't move vertically. The object's going to move parallel to the slope. So we have to break weight up into components, which is what we're going to do now, okay? So back to our object on the slope. We're not worried about weight, what the value is, but I do need to remind you of something. Weight, Fg, acts vertically down. The equation is mass times gravity. So the first thing we take note of is this. They're not necessarily going to give you the value of weight. You will have to work it out. They'll give you the mass, okay? So if I now draw in a set of axes, like in mass, the x and y, but I'm not going to make it normal vertical and horizontal. Vertical and horizontal, other way around. Okay, I'm going to draw it according to the slope. So now I have a parallel axis and I have a vertical axis. So I can take Fg and break it up like the vertical and horizontal components, but I'm going to use parallel and perpendicular instead. So part of weight is parallel to the slope. That part is what pulls it down the slope, and it always pulls it down. That can never go up. Why? Because gravity acts down. Instead of drawing it there, I'm going to pull it down. It's the same value. It's the same thing. It's parallel underneath. Fg parallel. That parallel sign you know from maths. Okay, use it. Then we have Fg perpendicular. That's the perpendicular sign for maths. This one, okay, is the force that's perpendicular to the slope. Okay? It's at a right angle to the slope. This angle, this is what makes this so special. We're not going to do all the geometry. Is always the same as the angle on the slope. Whatever the angle theta is there, that's what this is. Why do we need to draw this? The perpendicular force is important for the normal. When we look at friction, that becomes important. The parallel force is also important to know what's making the object move down the slope, okay? Will be important when we look at friction, will be important when we look at Newton's second law, so it's important. But we need to be able to work these out. So just like we did with the last ones, we're going to look at it in terms of trig, okay? The parallel force is opposite theta, so we're going to use sine. So sine theta is Fg parallel over Fg. So to get Fg parallel on its own, we're going to use Fg sine theta, okay? Because it's opposite. Then we need to do the perpendicular, okay? Perpendicular, it's adjacent to the angle. So, whoops, I'm starting from the wrong place. Let's just get rid of this. There we go. Cos theta is FG perpendicular divided by FG. So FG perpendicular is FG cos theta, okay? Now, because we're using FG, I can work out weight separately. But sometimes we don't want to do that because it's just lots of work on the calculator. You will sometimes see it written like this. mg sine theta. mg is weight. It's okay. We can do it in one equation. Same there. I can put mg in if I want to. All right, so don't get too fussed about that. I want to encourage you. Don't learn the equations. Learn how to use the triangle. I still do that. I still go, it's opposite, so it must be sine. It's adjacent, so it must be cos. I use the triangle because it's that way I know I can't get it wrong. I don't have to try and remember 4 equations now. We've done 4 equations today. We don't want to remember all 4. It's a lot of remembering. Okay, so we've done the components. In the next section, we're going to do a couple of calculations. Okay. Welcome back. So we are still busy with components, okay? Now, last time, well, in the last section, we looked at vertical components, horizontal components, parallel, and perpendicular. Now we need to do a question, okay? So the question is going to be about what happens when we have 2 forces on an object. So I showed you with 1 force, but how do we use these vertical and horizontal components? And the whole point of them is to find a net force, okay? That's what we're looking for. So here's what we've got. I've got 2 forces acting on an object. One is 120 newtons bearing 70 degrees. The other is 160 newtons bearing 40 degrees. The question is to find the net force. In other words, what's the result of these 2 forces if I put them together? We need a diagram, okay? So let's see how they look on a diagram. Bearing means that I'm measuring like a compass. So I'm going from north, which is 0, and I'm measuring an angle of 70 degrees. This is different from maths. In maths, your 0 is horizontal. For bearing, this is from geography, your north 0 is at the top, okay? So we have this. We have, I'm just going to give my bearing lines. My first force is 120 newtons bearing 70 degrees. So it would be 70 degrees and it's here. So there's my first force, and that angle there is 70. Okay? The second one, and I'm going to use this just so you can see the difference, is 40 degrees. So it goes there. And that's 160. I should have drawn my diagram a little lower because that's not big enough, but it's all right. There's F2, and that angle is 40. Now what I want to know is what's the resultant, what's the net force. So in other words, if I took those 2 forces away and I put a single force that will do exactly the same thing, where is it? I don't want a diagram. I want us to use components, okay? So that means I'm going to take the first one, F1, split it up into 2 components. Then I'm going to take the second one, and I'm also going to split it up. And then we'll do the next step. So step 1, split them up into 2 components. Keep drawing diagrams. I know sometimes we go, oh, but they're not for marks, I don't want to. But do it. Because remember, when you draw a diagram, you're not going to make a mistake. And even for us to sit and go, no, I can imagine it, I can see it in my head, sometimes our imagination doesn't work so well. Okay, so let's go back here. Let's do F1, okay? So F1 is there. I haven't done it quite to scale. This is going to make it easier. This was 70 degrees. We can use the 70, doesn't matter, but we generally go from the horizontal. So let's make sure that you know what that means. This angle, the two sides, the vertical and horizontal, are 90 degrees to each other, so this is 20. Be careful. I see that as 30 often, okay? We have vertical component. Now, I'm working with two forces, F1 and F2. I need to make sure I remember which vertical and which horizontal goes with each. So this is going to be F1 vertical, and this one here is going to be F1 horizontal. That way, that means once I've got them, I know which one's which. It's easier for me to work with, okay? Let's start with the horizontal. Horizontal is adjacent. That means I'm going to use cos. So, cos, I'm going to go straight here. So my horizontal is F cos theta, okay? If you want to go cos theta is a horizontal over F, that's fine. Doesn't matter. We need to work it out. F1 was 120. So that's 120. We're using 20 degrees. Now, my maths is good, but I can't do this in my head. So we're going to use the calculator. Okay, so remember, we're doing 120. Okay, 120 times cos, and our angle was 20 degrees. Don't forget to close your bracket. And we get 112,76. Your instructions in any exam round off to at least 2 decimal places. You can use more, but 2 is fine. So it's 112,76, okay? So now I'm going to put it here. 112,76 newtons. It's a vector, which means I need direction. If I look at this, this was bearing, okay? I need to say bearing 90 degrees, because this is, the 90 is here. Okay, so here, bearing 90. Okay, there's no marks for this bearing answer yet, but I need it for later on. I've got to keep track of all the directions, okay? So, and I'm not sure why that ended up on this side, but it's all right. We'll go with it. What I'm going to quickly do is take this out so that I can do the horizontal, the vertical here. Okay, now we're going to do the vertical. There we go. So now, over here, vertical is opposite. So F1 vertical is F, opposite means sine theta. So now we're going to do 120. I don't know why I'm putting a degree sign there, because there isn't a degree. So let's take that out. No degree there, but it's sine 20. And again, we'll need the calculator. Okay, so let's just clear that, because that's not what I'm doing anymore. So now this is 120, whoopsie, extra numbers, 120, sine 20, and it's 41,04. Okay, I'm not going to use the 2. Doesn't actually matter. So this is now, oh, there we go, 41,02 newtons, but this is now up, so this is bearing 0. We good? We've only found the components of the first one. Now we need to do the second one, okay? So the thing about these questions is they're long, but we get a very accurate answer. So F2, let's just remind ourselves, was 160, and this angle was 40 degrees. Okay, so that's the way it looked. Now when we do our components, we're going to have F2 horizontal, F2 vertical. What do I need? I need the angle in the middle. So we remember that they're perpendicular. That makes this angle 50. Okay, be careful with that. Be very careful. Starting with the vertical, it's opposite, so we're going to use sine. So F2 vertical is F2 sine theta. So that means, and again, oopsie, sorry about that. Let's just go back to where we were. I'm having fun with the board today. I put a degree sign in there, and I don't know why. So let's just take that out, because we should. And so this is sine 50. That's where the degree goes. Calculator. Okay, let's get rid of what we had there. So now this is 160, and it's sine 50. And it's 122,57, because that's 67. It's going to round up. So, okay, I'm too fast for the board. That's what's happening. Now I've forgotten what the answer is. There we go. 122,57. 122,57 newtons. This vertical is also up, so it's bearing 0. Okay, so it's vertically up. So now we've done the vertical. Now we need to do the horizontal. Horizontal is adjacent, so we're going to use cos. So F2 horizontal is going to be F2 cos theta, which is 160 times cos 50. Going to use the calculator. Okay, so now we have, we're going to get rid of that. So we have 160 cos 50. Close the bracket. 102,85. Now I'm going to try and remember that. 102,85. Here we go. 100 and stop it. 2,85. Which direction? Bearing 90 degrees. Okay, so right now, some of you are looking at this and going, that's nice. You haven't gone anywhere. I actually have. Okay, so what we have found out is this. We have a vertical component from the first force that's bearing 0 degrees, going up. We have a vertical component from the second force that's also bearing up, going upwards. We have a horizontal force from the first one, which is going 90 degrees. And we have a horizontal force from the second one that's also going at 90 degrees. Now, I've drawn them the same size, but they're not the same size. I'm not worried about that. It's about the direction. I can now take these 4 forces and make them into 2, because what we're going to do now is I'm going to take those 2 vertical forces and I'm going to add them together. I'm going to take those 2 vertical forces, horizontal forces, and I'm going to add them together. I'm going to find a resultant of those 2, okay? So I'm going to take that away because I'm sort of running out of space, okay? I want to keep these values that I've got over here so that you remember them. Those 2 go in the same direction, so this is what we're going to do. I'm just going to get rid of this because I don't need this now. So what I'm finding is the first thing I'm going to find is F net vertical. So I'm going to add my first vertical with my second vertical. Now the first vertical we worked out earlier to be 41,22. This vertical is 122,57. Now, at this point, you are welcome to do that in your head. However, in an exam, you normally get quite stressed, so use your calculator, okay? Okay, so we got 41.22 plus 122.57, and no fractions, we don't like fractions, so this gives me 163.79 newtons. It's a vector, so I need a direction. And this one was the vertical one, so this is bearing 0 degrees. All right, we've done the net vertical. Now we need to do the net horizontal. So that I'm going to do now. I don't need this answer anymore. And you're doing this all nice and neatly in your notes underneath each other. And we don't need this anymore either, so let's get rid of this. All right. So, net horizontal, which means I'm going to add the first horizontal with the second horizontal. The first horizontal we worked out to be 112,76. The second one is 102,85. We're going to add these together. Let's move this so that we can actually see it nicely. So we've got 112.76 plus 102.85. Again, can't use fractions, make sure it's a decimal, so we have 215,61. So 215,61 bearing 90 degrees. And once again, you are probably still looking at me and going, really? We still haven't finished. No, we're not. But we're almost done, because now we're going to old-fashioned vectors. What have we actually worked out? Well, now we know that we have a vertical force that goes up of 163,79, and I have a horizontal one of 215,61, and I can find the resultant. My resultant is there. So I want F net. Let's make that F actually look like an F, and not, I don't know what that looked like. It's a right-angled triangle. We're going to use trig. Now, we are going to use Pythagoras to find F net, and then we are finally done. So, let's use Pythagoras square of the hypotenuse, so that's F net squared is the sum of the square of the opposite two sides, horizontal. And actually, I don't need the 1 and the 2 there because we're using the net values here, okay? So we really should put net there. The only thing with this section is it gets a little horrible with all the writing. Like, things get big, but it doesn't matter. So my vertical was 163,79. My horizontal was 215,61. Okay, I definitely can't do this in my head. So let's put this in the calculator. So we're going to go 163.79 squared plus 215.61 squared. there, oh, no, or not. Let's do that again. 163.79 squared plus 215.61 squared. We have an answer, but I need to square root it. So I'm going to square root the answer, and I get 270.77. Again. All right. 200, let's just check again, 70.77. One last thing, because we're not done yet, but I promise this is the last thing. We're working with vectors. Vectors mean that we need an angle, we need a direction. So we need to know theta. Right angle triangle, we're going to use the opposite and the adjacent, so we're going to use tan. So tan theta, my opposite, which is my horizontal, over my adjacent, which is the vertical. So tan theta is going to be 215.61 divided by 163.79. All right, so back to our calculator. We're going to use second function tan, because we need tan to the minus 1. We're going to put in the right numbers, 215.61 divided by 163.79. Close your brackets, don't forget to do that. Gives us 52.78 degrees. Okay, so we have 52.78 degrees. We need to write it as a sentence. So my F net, 270.77 newtons, bearing 52.78 degrees. And now after that very long question, we all deserve a break. So I'll see you in a bit. Welcome back. I hope you're refreshed. We're going to do one more question, okay? And I promise it's not as long as the last one. Okay, so just to remind you what we're looking at today. We're looking at components, okay? So we've been looking at forces, and we're particularly looking at components. So let's look at one that's a little simpler than finding the net force. Okay, so what we have is we have a lady waiting for a taxi. She's pulling a 20-kilogram suitcase with a strap. So she's pulling it at an angle at a constant velocity. So now the constant velocity is quite important because it means when we look at it, constant velocity, there's the constant, that the forward forces and the backward forces are equal, okay? Makes an angle of 30 degrees to the horizontal. She pulls on the strap with a force of 35 newtons. Frictional forces between the case and the floor cannot be ignored. She can only pull it at constant velocity if there's friction, okay? Because if there's no friction, it'll accelerate. So the 35 newtons is at an angle, and I actually have a diagram for us, okay? So we're concerned with what's happening there. It's at an angle. Remember, the suitcase is moving horizontally, so it's the horizontal forces that are important for us. First question, draw a free body diagram. Free body diagram means a dot, to indicate all the forces exerted on the case in both the vertical and horizontal directions. Now, this is a different type of question for you, because I don't want the 35, because that's at an angle. I want the other forces. So let's start with the easy ones. First of all, we have the dot. It's going to be FG, vertically down. Because there's gravity, there's going to be the normal force. That's easy. There's friction. Friction is going to oppose her motion. Now we've got to think about the force that she was pulling it at. Remember, it was at an angle. That means we have a horizontal component that's going to the right and a vertical component that's going upwards. That's what they want on this one. They don't want the one at an angle. So here we have the horizontal component, and there we have the vertical component. Please be careful here. I know the normal force and the vertical force are both horizontal. You get very tempted to draw one line and put two arrows on, saying one's for the vertical and one's for the normal. Please don't do that. You must draw them as two separate forces. I must see them separately, okay? I know they're going in the same direction, and I know they'll add to each other, but they're not the same force, so we need two arrows for them, okay? And what we need to do is, I'm just going to make my dot a little bit bigger, because the forces must touch the dot. Please be careful with that as well. They must touch the dot because they're coming from that center point, okay? So now we've done the free body diagram. Now they say, calculate the component, so either the vertical or the horizontal, that will tend to move the case over the floor. It's going horizontally, so it's the horizontal component. Remember, we've got 35 newtons. This was 30 degrees. We want the horizontal component. Horizontal, it's adjacent, so we're going to use cos. So the horizontal component is F cos theta. So it's 35 times cos 30. I definitely cannot do this in my head. So let's clear my calculator. So 35 times cos 30 is 30,31. And she's going to the right. So we're going to put to the right. Done. See? Much easier question. And we're done. Yes. Bet you thought we wouldn't get a question that easy, but we are done. Okay, so just remember, when we do the summary, when the forces are at an angle, we have two components, vertical and horizontal. When we have an object that's on a slope, the weight has two components, parallel and perpendicular. And we are done for this lesson. Well done, and I'll see you next time.